Hi everyone, Mr. Roloff here, and today's lesson we're going to be looking a little bit at balancing chemical equations and why that's important for us in chemistry. It's going to be really handy to have the homework sheet here, what goes in must come out, available, because what we're going to do is first we're going to talk about these first three questions in the notes, and we're also going to be doing a couple of actual problems from the homework, so please follow along with me. So the first thing we want to do is we want to identify what is a chemical reaction. So a chemical reaction is the process by which one or more substances change to produce one or more different substances. So basically what that means is we're taking something and it's going to change into something else. And that's a really simple way of describing what a chemical reaction is. How do we know when a chemical reaction has taken place? We actually answered this at the start of the year. See if you can kind of remember, how do we know? This is actually day one. We did some demonstrations for you. How do we know a chemical reaction has taken place? Can you remember any of those things? Maybe I can get you started. Color change. Maybe you remember energy change, odor change, anytime we have bubbles. And then our last one here is a precipitate. So we're going to see that in lab eventually here, but precipitate forms when we take two liquids and we end up with a solid, actually. So 5 indicators that a chemical reaction has taken place, and again we'll look at those more in depth once we get to the lab. So what is an actual chemical equation? You've probably seen them already in class, but what are they? What do they do? Well, I've got my picture of Gordon Ramsay here. Love this guy. He's very real. He tells it like it is, but he's all about recipes. He's all about making things taste good, and our chemical reaction is really just a great big recipe. So it tells me what's going in here. On the left side, these are our reactants. So these are going in. These are like our starting ingredients when we're cooking. And what comes out would be our products on the left side. So we really have 2 parts here. You should know the reactants and the products. And recognize here, if I point out just like this carbon, this black carbon atom, see how there's 1 carbon atom. We don't write the ones, but there would be a 1 down here in the formula. There's 1 carbon atom here. I see 1 carbon on the right side. So it's equal, it's balanced. If I look at the oxygens, I have 1, 2, 3, 4 oxygens on the left, and I have 1, 2, 3, 4 oxygens on the right. So it's all balanced. All we did was basically rearrange how those molecules are fitting together. Now, when we go to balance something, so just like you can see here, if I start with CH4 and O2, I can't change the number here. So I can't change the little number. I can't change, we call that the subscript. If I do that, I'm changing what the molecule is. So, if I count these up, let's say that I have, I don't know, if I only have 2 oxygens over here, O2, basically this would get screwed up because I have, if I ignore this 2 in front, I have 1 oxygen there, 2 oxygens there, so I have 3 oxygens on one side and only 2 on this side. So we use the coefficients to help balance that out. So if I put a 2 in front, now I have 4 oxygens, and I look over here, now 2 oxygens there, 2 oxygens there, so I have 4 on the left, 4 on the right, which is what we want. So our first and probably the easiest method would be just to literally count the atoms. And typically when I do these problems, what you'll see me do is I'll put a line right here where the arrow is, because remember that divides our reactants on the left and our products on the right. So what I'm going to do now is I'm just going to count up how many atoms I see. So for my hydrogen, again, I'm looking at these subscripts here. These little numbers tells me I have 2 hydrogens. And my chlorine, I also have 2. On the left side, look at the right side though. My right side, I have 1 hydrogen and I have 1 chlorine. How can I get that to balance so that I have 2 on both sides? Well, you probably recognize that if I put a big 2 here, I can't change this. I can't put like little 2s here. That ruins it. It's not HCl anymore. It's something totally different that really doesn't make sense. So I'm just going to erase those. All I can change is putting numbers in front. So at this point, I could either leave these blank, or because we're lazy chemists, we don't write ones, but we could always put them in there if we'd like. So the balanced equation for this would be 1, 1, 2. And what adding this 2 does, what adding that 2 does is it basically takes our 1 and it's going to multiply. It's going to distribute to not only the H, but also the Cl, because they're tied together. So if I kind of do some quick math here, 2 times 1, so they're both, you'll notice, 2 on the product side and 2 on the reactant side. So now we're balanced. Now, just counting them up works sometimes. I usually use this method. This is called the seesaw method. It is the way that I kind of describe this. And what I like to do is kind of bounce back and forth. If you know what a seesaw is, it kind of goes up and down, back and forth. And so the first pro tip that Mr. Rogers here has for us is to put a 1 in front of the most complicated compound for a place to start. These might be, I don't know, note sheet worthy, these pro tips here. Probably a good idea to have those somewhere for later reference. But if I put a 1 near the most complicated compound, or sometimes even just the first compound, leaving the lone elements for last. So where's our lone element? Pro tip number 2. Maybe you see that our oxygen is all by itself. So I'm going to leave that for last according to this pro tip. So leave the oxygens for last. I'm just counting still. All right, I've got 1 carbon over here. Once that 1 distributes, on the right side, I also have 1 carbon. So far, so good. The carbons are good. So now the seesaw, I'm going to go back over here. Now let's count the hydrogens. So my hydrogens, I've got 4. And how many hydrogens do I have over here? Oh, only 2, right? So I'm going to double that. So I'm going to multiply that by 2 to get 4. So my coefficient is going to be that 2. Now that not only affects the hydrogen, but it also affects the oxygen. So now that I have the carbons and the hydrogens done, let's do what our lone element we left for last. Our oxygen, we have 2. Over here, our oxygens, we have, let's see here, I'm just counting these up. I have 2 from the CO2, and then I have 2 times 1 would be, so I've got 2 plus our 2 times 1, which gives us 4. So notice we're not balanced. I have 4 oxygens on the product side. I have 2 oxygens on the reactant side. So what do I need to do? Multiply that by 2. My CO2 can stay the same. So my balanced formula would be 1, 2, 1, 2. So let's take a look at another problem where we might end up with an odd number of atoms on one side and an even number on the other side. Let's focus on number 8. By the way, if you haven't noticed, we have been doing problems off of that practice sheet, number 6 and number 15. So if you need to go back and just kind of fill that in as we're going along here, that's a good idea. But I'm just going to go through. I'm going to do the seesaw method once again and put a line separating my reactants and my products. Now when I go to count these out, I'm going to put a 1 next to the KClO3, and I'm going to try to balance everything off of that. So for K, I have 1. Over here for K, I also have 1. So far so good. For Cl, I have 1. And my Cls, I have 1. So far so good. Everything's balanced. But when I look at those pesky oxygens, our oxygen, I have 3 on the left side. I have 2 on the right side. I left my O2 for last, just like Rogers told me on the last one. Leave that lone element for last. How do I fix this? there's nothing I can really put in front to make that work out. Or is there? I'll kind of come back to that. If you can do that mathematically in your head, the decimal does work. You could put the decimal in there, but let's follow Serena Williams here. If that math kind of eluded you, our pro tip number 3, if you see odd and even, you'll hear me say this a lot, we're going to double what you know. We're going to double what you know, and I'm just going to add that in here. Double what you know. And basically what that's saying is we're now going to double the odd numbers. So we're going to, instead of 1, we're going to change this to we're going to double it. Now it's a 2. We're going to double this. Now it's a 2. Let's see how our numbers work out. And I always like to start over here with the counting just to make sure. So my 1 is now a 2. That should be a 2. The CL should be a 2. Oops. 2. My CL should be a 2. But look what happened to my oxygens. Now, on the left side, my oxygens are 6. Well, 2 times what gives me 6? 2 times 3 gives me 6. So we now have this balance. Now, what I said before, if you were able to do this in your head mentally, you could have said, well, 1.5 times 2 would give me that original 3. If you can do that in your head, I would also take the decimal form. Why? Because you can have a half a mole. Just like in our recipe, we could take a half of a teaspoon, a half of a cup. You could have a half of a mole. You could have 3.01 times 10 to the 23rd atoms. So we will take the decimal form as well if that's easier for you. So one more tip here from LeBron. He says to keep the polyatomic ions together. Now remember what this means, polyatomic ions. Poly, hopefully we remember, means many, and then atomic is just atoms. So keep the many atoms together. What I'm saying there is when we go to count this, so I'm going to still use my seesaw method, left and right. My CU, let's follow that pro tip of putting a 1 next to the scariest element, the thing that worries us the most. And for me, there's a lot going on this one right here. There's parentheses, there's multiple subscripts. So I put a 1 next to that, and I'm just going to start balancing it off of that. So my CU, I have 1. Over here, I'm going to balance that out. So my coppers also have 1. And now, instead of breaking this down and saying, look, there's 2 nitrogens, there's 6 oxygens, what I'm going to say is I'm going to try to, notice how there's a NO3 on this side, and there's an NO3 on this side. Now, this doesn't always work, but sometimes we can get away with keeping those together. So if I have 2 NO3s, do you see how I can double this times 2 to give myself 2 NO3s on the left and 2 NO3s on the right? Now notice that 2 not only applies to the NO3, but it also applies to the AG. So that coefficient applies to everything. So our AG now is 2 on the left. Well, we left that as a lone element there. We can take our 1 and multiply it by 2 by putting a coefficient of 2 in front. So this one becomes pretty easy. You don't have to worry about distributing the 2, to everything. If you just try to keep that NO3 or the polyatomics together. So let's try one more. This one's probably the most difficult that you would see, say, on a test. The first couple are pretty common as far as what we're going to be testing you on, but this is kind of our A-level problem, if you will. Again, I'm going to put my line here, and I'm going to try and seesaw this. Again, I'm going to put a 1 in front of the scarier element here. We got a bunch of carbons and hydrogens that are broken up, and I'm just going to start balancing from that. So my carbon on this side, I have 1. My carbon on this side, I have 1. My hydrogens on the left, I have 4. And over here, my hydrogens, I only have 2. So I'm going to put a 2 in front of that. So I get that up to 4. So it's balanced. Now the oxygens. The oxygens in this one are pretty tricky because I'm trying to figure out what goes in this space. Now, when I add these up, I'm just going to add the right side up first because I have 1 times 2. So my 1 times 2 gives me 2 oxygens. But then there's some more over here. Be careful when they're split up like this. Don't forget, in this case, we've got 2 times 1 oxygen gives us 2 more. So I actually have 2 plus 2, so I have 4 on the right side. Now, on the left side, we have, also be aware here, oxygens that are split up. So in this case, 1 times 1, that's pretty easy math. We've got 1 plus 2 times something, right? So 2 times our coefficient. So what I'm going to do is I'm actually going to set this up almost like an algebra problem. All right, so if algebra is really scary, don't let it be very scary. We can figure this out. All I'm going to do, just give myself a little bit more space here for my algebra problem. I'm going to take 1 plus 2x equals 4. Solving for the 4, if I am adding 1, I do the opposite. I'm going to subtract 1 from both sides. So 2x equals 3. 2 times x, do the opposite to get x by itself. So my x is 1.5. And if we wanted that to be a whole number, we could multiply everything by 2, just kind of like you saw in pro tip number 3. So that would be our best method of solving this. Now, if you recognize, like, hey, I've got an odd number and an even number, and you end up doubling, let's say that you put a 2 here instead. Well, now we've got 2 carbons, we have 8 oxygens. Over here, we would have now, instead of 1, we'd have 2 carbons, and we'd have, instead of 4 oxygens, we double that. 4 times 2 gives us our 8, and this would be a 4. And now we're left with our oxygens again. Well, now it's 2 plus 2 times something, so 2 plus 2x equals, over here it would be, what would it be, 4, and over here would be 4. So 4 plus 4 is 8. So the math works out a little bit better, or a little bit easier, I guess you might say. If I do this kind of over here in the margin, 2 plus 2x equals 8. Subtract 2, we get 6. 2x equals 6. Divide both sides by 2, x equals 3. So either way, I would accept both come test time or even on the homework, okay? So hopefully that helps. That's obviously our most difficult problem there. What we would like you to do is to try the odd or the even and submit that. Ask your instructor if you have any extra questions. Thanks.